Hello everyone, this is Radio Geek Garage. Recently, I was browsing YouTube for videos about antennas and noticed that the platform is overflowing with videos on how to make a loop antenna with a shield break. There are dozens of them, and it seems like many creators are just copying each other's content and posting their own versions. However, none of these videos actually explain how this antenna works. They simply show how to build it without understanding its working principle. But this antenna is quite interesting. That's why I decided to make a video that explains how it operates. This might be the only video on YouTube that actually breaks down the functionality of a coaxial loop antenna with a shield break. First, let's acknowledge that there are many different types of coaxial loop antennas. You can see some of them on the screen. Despite their similar appearance, they differ significantly in both working principle and intended application. Some antennas are designed to receive and transmit the electrical component of a radio wave, whether horizontally or vertically polarized. Others are designed to work with the magnetic component. These can be standalone magnetic antennas, coupling loops within a main antenna circuit, or even impedance transformers. The antenna we're discussing today is specifically designed to work with the electrical component of a horizontally polarized radio wave. But to fully understand how it works, let's start with a simpler example. One of the most basic designs is a magnetic loop antenna made from coaxial cable, where the shield covers the entire length. The central conductor at the end of the loop is connected to the shield of the feeder, while the shield's end remains open. Originally, this type of antenna was designed to receive the magnetic component of a radio wave, with the coaxial shield blocking the electric component. However, this design is flawed. A significant potential difference appears at the open end of the shield relative to the central conductor, meaning the electric component still affects the antenna. Moreover, if this antenna is used to receive the electrical component, it lacks proper impedance matching. At the open end of the shield, the voltage reaches its maximum, while the central conductor should have a current maximum at that point. This imbalance results in poor performance as both a magnetic and an electric antenna, essentially a waste of resources. To fix the issue of potential buildup at the end of the shield, the next step is to connect the shield's end to the feeder along with the central conductor. On the plus side, this fully shields the inner conductor from external electric fields and improves impedance matching. However, it also creates a shorted loop, preventing the antenna from effectively working with the magnetic component. As a result, this design is completely ineffective. It cannot properly receive either the electrical or magnetic component. A completely useless configuration. However, take note that current still flows along the external surface of the shield. Let's assume we are dealing with horizontal polarization, as in TV signals, where the electric field induces current on the loop surface, creating maximum current at the top and bottom of the loop. However, this current does not enter the inner conductor of the cable. So how can we transfer this external shield current into the cable without disrupting the antenna's symmetry or impedance matching? The solution is to introduce a break in the shield at the top of the loop. This is a very effective and well-thought-out approach. The break allows the current from the shield's exterior to enter the inner conductor. Let's take a closer look at this process. On the outer surface of the shield, to the left and right of the gap, currents I1 and I2 are flowing. When they reach the break, they have no choice but to flow into the inner surface of the shield, becoming currents IA and ID. Once inside, we can confidently say the currents have entered the cable. The current on the inner surface of the shield, which acts as one conductor of the transmission line, induces a corresponding current on the surface of the central conductor, the second conductor, known as currents IB and IC. Thus, the shield break serves as a coupling point where the current from the outer shield enters the cable. Even though the central conductor is fully shielded from external fields and does not directly receive a signal, the current distribution inside follows the same pattern as a standard loop antenna. The current maxima occur at the top and bottom of the loop, making the antenna appear balanced and impedance matched at first glance. However, since it is connected to an unbalanced transmission line, it is recommended to use a balun, a choke, or at least a U-bend for proper operation. Another important point is that the antenna's impedance is higher than 75 ohms, ideally around 200 ohms, though usually lower in practice. Ideally, a matching transformer should be used, though this is often overlooked. The key advantages of this antenna include 1. Ease of construction, even someone with no deep understanding of its working principle can assemble it as long as they have the right cable. 2. Better impedance matching with low impedance cable compared to a folded dipole or a standard loop antenna. However, the reason for its low impedance is not necessarily an advantage. The main drawback of this antenna is that it is always detuned, meaning it is not resonant. Because of this, its active resistance is lower than it would be at resonance. Why is it detuned? The wavelength on the outer surface of the shield and inside the cable do not match. On the outer surface, the shortening factor is minimal around 0.95, whereas inside the cable it can be as low as 0.6. This makes precise tuning difficult. As a result, its gain is lower than that of a standard loop antenna. However, the detuning does provide one benefit: a wider bandwidth. Thanks to this, the antenna is well suited for receiving multiple channels, such as those in the digital TV frequency range. This is its most common application. Now let's summarize. 1. A coaxial loop antenna with a shield break at the top is designed to receive the electrical component of horizontally polarized radio waves. 2. The shield break acts as a coupling point where the current from the shield's outer surface enters the cable. 3. The antenna is structurally detuned from resonance, making it relatively broadband but with lower gain. I hope this explanation clarifies how this antenna works. So far, I haven't seen a proper breakdown like this on YouTube. If you found this video useful, give it a like, subscribe to the channel, and leave a comment with your suggestions for future topics.